Let's take a look now at an intro to rational expressions. So let's begin with the definition. Let's have f and g be polynomials. So let f and g be polynomials. There's no restriction on what polynomials they are, their degree, their coefficients, nothing, just as long as they're polynomials. An expression f over g is called a rational expression, so long as the function g is not identically 0. Okay? So a rational expression is essentially a fraction made up of two polynomials, one in the numerator, one in the denominator. Okay? Of course, we don't want the denominator to be identically 0 because division by 0 is undefined, but otherwise, any polynomials can be divided out for a rational expression. Okay? So, for example, let's say we have x squared over x squared minus 4. That's a rational expression. It's a polynomial over a polynomial. I can change the powers in the numerator or the denominator or both. They don't have to be the same. There we go. That's a rational expression, a polynomial over a polynomial. Of course, a polynomial can have more than one terms, right? So here we can say something like x minus 5 over x squared minus x minus 20. And that's a rational expression as well. Note that a constant is also considered a polynomial. It's a polynomial with one term and with degree 0, but it is technically a polynomial. So you just have a regular whole number divided by a polynomial. That also qualifies. All of these are rational expressions. The one that we don't generally consider a rational expression is something like this, where you have a polynomial in the numerator and then just a whole number in the denominator. The reason we don't generally consider this as a rational expression, even though it does meet the definition, is because this could be thought of as something much simpler. Here, if we just do the division, that's equal to 1/10 x minus 5 over 10 is 1/2. Notice that's not really a rational expression because we can simplify it down to give us just a regular polynomial. All right? So here, this where your denominator is just a constant is usually not considered if the denominator is constant without any variables. This is considered a polynomial. Not a rational expression. So, as mentioned before, a rational expression is basically just a fraction where your numerator and your denominator are some form of polynomial. Okay? Well, if it's a fraction, then remember, 0 cannot be in the denominator. But see, here's the thing. These polynomials have different values. Any polynomial can equal to 0 sometimes. Well, almost any polynomial could equal to 0 sometimes, right? If you're using only real numbers, sometimes things can't be solved. But generally, if you say, I have a polynomial and I want to make sure it's not 0, you can't do that for all real numbers because this is going to change depending on the value of x. So whenever we talk about a rational expression, one thing we have to do is we have to talk about what values are we not allowed to plug into it. Because again, this is a fraction, and if the denominator is 0, then this doesn't make any sense. So every rational expression will have some numbers that cannot be plugged into it. There are some numbers that x cannot be. So another note, any values that make the denominator equals 0, are restricted. They're not allowed from a rational expression. So for example, let's go ahead and find all restrictions of this rational expression. I'll go ahead and use this first one here. Find all restrictions of a rational expression. All right, and I'm going to go ahead and use this one here. X squared over x squared minus 4. Now, note that we don't care what's in the numerator. The numerator can be 0, it can be positive or negative. The numerator of a fraction can be anything. What we don't want to have happen is the denominator equal to 0. All right? Looking at this denominator, we can find where it's equal to 0, and that will tell us what we're not allowed to use. So let's go ahead and do that. Well, let's take x squared minus 4 and set that equal to 0. Again, we don't worry about the numerator. The numerator can be anything. It's the denominator that has to be restricted. All right, so let's see. X squared minus 4 is equal to 0. Here I can go ahead and add 4 to both sides. And so there we go. I'm solving for x plus 4. It's going to give me x squared equals to positive 4. And now I can take the square root of both sides. So I'm going to have square root here and square root here. Now, when I take a square root, there's two different square roots. There's a positive and a negative, right? If I take 2 and I square it, I get 4. But if I take negative 2 and square it, I also get 4. So there's two different answers, a positive and a negative. So here, x is equal to plus or minus 2. And remember, plus or minus means there's actually two answers. It means x is equal to positive 2, x is equal to negative 2. Those are my two answers there. So those are the two numbers that make this expression 0. In fact, you can even try it, right? 2 squared is equal to 4, minus 4 is 0. Negative 2 squared, negative 2 times negative 2 is positive 4, minus 4 equals to 0. So those are my two results. What that means is this expression can be evaluated for any number except for these two. So these are my restrictions. This expression can be evaluated for any value of x except x equals 2 and x equals minus 2. Because if you use x equals 2 or x equals minus 2, that means your denominator is 0, and so the expression is undefined. Note you can evaluate it for anything else, so keeping with the same example, let's go ahead and evaluate I don't know how to spell. Let's try that again. There we go. Evaluate the expression for x equals, and we'll be able to use any number. Any number will be valid except for either of these. So let me just choose the number 4. Okay. In that case, I'm going to have 4 squared. I'm going to go ahead and put it in parentheses just to highlight the fact that that's the number that I plugged in. Over 4 squared minus 4. And here that's 16 in the numerator, 16 minus 4 in the denominator, which is really 16 over 12. And then I can actually reduce that, dividing the top by 4 and the bottom by 4. And there we go. So we could do that with any number. We can evaluate the expression for any number. We could say evaluate for x equals to 5, and you plug in 5 and simplify. You could evaluate for 7 or negative 4. If you want to, you can use a fraction. You could do 1/2. The only numbers that are not allowed are those two there. Right. Let's see that again. Let's take another expression. And we're going to do two things with it. We're going to find all values for which the expression is undefined. This is another way of saying this. We're finding all restrictions. We're finding the values for which it's undefined. Those mean the same thing. We're going to find what values are restricted, which ones we can't use. Why are they restricted? Why can't we use them? Oh, because the expression would be undefined. So these are exactly the same question. We're doing the same process. All right, so our expression is going to be x minus 5 over 2x minus 5. Okay? Same idea. The numerator can be anything. If the numerator is positive or negative, fraction, whole number, decimal, or even 0, that's fine. 0 divided by some other number is 0. What we cannot have is we cannot have the denominator equal to 0. So here, note, numerator can be anything. There are never restrictions on what the numerator can be. In a rational expression. However, in the denominator, we cannot have this equal to 0. Cannot be 0. Okay, well, let's find out where it is 0. Let's find out what numbers make that 0, and that'll tell us which ones we cannot have. That'll tell us where our expression is undefined. 2x minus 5 is equal to 0. All right, let's figure out where that is. Here, we can add 5 to both sides. That'll give us 2x equals to a positive 5. And then I can go ahead and divide both sides by 2 to isolate our x. Here 2 divides 2 to give me 1, which is what I want. I want 1x equals 5 halves. So there it is. This is the only value, and for this one there's only one. This is the only value for which your expression is undefined. Note that we could evaluate this for any other number. We could evaluate it for x equals to negative 5 halves. We could evaluate it for x equals 0. We could evaluate it for x equals 400. Doesn't matter. Any number except for that one. So here, let me go ahead and do that. Let me go ahead and evaluate. This is a separate example. I'm just going to go ahead and use the same expression here. We're going to evaluate the expression x minus 5 over 2x minus 5 for x equals to 0. Now you might say, well, wait a minute, I thought we couldn't have 0. We can have the number 0 plugged in. What we can't have is, once you plug in the number, you can't have a 0 in the bottom. So if we plug in 0 here, that's going to give us 0 minus 5 over 2 times 0 minus 5. The numerator is 0 minus 5, which is a negative 5. And here 2 times 0 is 0. 0 minus 5 is a negative 5. So notice, we can plug in the number 0. That's okay. As long as once you plug it in, whatever's left is not 0. All right? We plugged in 0, and that's okay, because even after we plugged in 0, our denominator was some other number, not 0. And then here we could simplify. Negative 5 over negative 5, that's a positive 1. So there we go. There's our expression. That's the value of our expression when x is equal to 0. And we could plug in 0. We could plug in 1. We could plug in 5, negative 1 million. Any number, as long as it's not this one. Okay. So go ahead and give this a try. I'm going to ask you 2 questions here. First of all, you're going to find all values for which the expression let's say 2x plus 3 over 5x minus 3. Find all values for which the expression is undefined. And evaluate the expression for x equals to negative 4. All right, so go ahead and pause the video and give that a try. Once you're done, go ahead and unpause and we'll go through it together. All right, let's go through this. The numerator can be anything we like, but this denominator must not be 0. So let's find what makes it 0, and that'll tell us what we can't use. Set the denominator equal to 0. We can go ahead and add 3 to both sides. That'll give us 5x equals to 3. And now we can divide both sides by 5. 5 divides 5 to give me 1. So here I'm left with 1x equals to 3 over 5. So this is our restriction. This is the value for which the expression is undefined, whichever we want to say that. And then the second part of the question was, now evaluate the expression for x equals to negative 4. Okay, so evaluate means plug in the number and simplify. So it's going to be 2 times 4 plus 3 over 5 times 4 minus 3. All right, 2 times 4 is 8 plus 3 is 11. 5 times 4 is 20 minus 3 is 17. And since those numbers don't reduce, 11 over 17 just stays 11 over 17. So here we have, this is the value for which our function is undefined, and this is the result of evaluating at x equals to, that should be positive, that should be negative 4, shouldn't it? So this was positive 4. Let me go ahead and do that correctly. Negative 4 times 2 is negative 8. Negative 8 plus 3 is negative 5. There we go. I can't read my own writing. I thought that was positive 4. And then over here, negative 5 times 4 is negative 20. Negative 20 minus 3 is negative 23. Like this. And here you don't reduce those. That's just negative 5 over negative 23. You can't reduce the numbers, but the two negatives do simplify out. So here negative over negative is a positive. So we can just write that as positive 5 over 23. And this is our result. All right? And that is our result. Now, one thing to note is you might not have any restrictions. Some expressions are such that your denominator is never 0. So, for example, same kind of question, find the restrictions of a rational expression, and let's say we have x over x squared plus 4. Okay. In this case, we would do the same thing. We would say the numerator can be anything, but we need the denominator to be something other than 0. So our restriction will be whatever makes the denominator equal to 0. 2x plus 4 equals to 0. Notice here that this doesn't have any solutions. There are no real numbers that make that happen. Because if I take 4 away from both sides, this will give me x squared is equal to negative 4. And then to get that x by itself, I need to take a square root. Whenever I take a square root, there's 2, there's plus or minus. But notice here, when I take the square root of a negative number, there are no real numbers that work that way. Because if I square a positive, I'm going to get a positive. If I square a negative times a negative is also a positive. And if I square 0, I get 0. So there are no real numbers that I can square to get a negative, which means here, this doesn't happen. So this has no real solution. Okay, but if there's no real solution, that means that this has no restrictions. Which means this expression can be evaluated for any and all numbers. It doesn't matter what number you choose, you will always be able to plug it in and simplify. So just keep that in mind. Not every expression will have a restriction. Not every rational expression will have a restriction because not every denominator can equal to 0. Now, when we think about a rational expression, what we should be thinking about is this is a fraction. That's why the denominator can't be 0, because fractions with a 0 in the bottom are undefined. Okay, well, what else do we know about fractions? Well, one thing we know about fractions is that they can be written in many forms. For example, the number 1/2 is exactly the same as the number 2/4, is exactly the same as the number 3/6, is exactly the same as the number 4/8, which is the same as 5/10, and so forth and so on. There's lots and lots of ways of writing any individual fraction, and these all mean the same thing even though they're written differently. Well, the same thing will be true of rational expressions. There are different ways of writing a rational expression. But whenever we write fractions, we don't usually write them any of these ways. Usually we write them in this form, which is what? This is in lowest terms. The smallest numbers that in combination mean the same thing. Well, how do we find the fraction in lowest terms? Well, we reduce. What we do is we take something like 12/16, that's a fraction. But to write it in lowest terms, what I can do is I can factor out the numerator and denominator. So as a quick review of how to reduce a fraction, if you take 12, 12 is 2 times 6. And even though 2 is a prime number, 6 can be factored as 2 times 3. So here the prime factorization of 12 is 2 times 2 times 3. 16, well, 16 is 4 times 4. And each of those numbers can be factored further as 2 times 2. So 16 factors as 2 times 2 times 2 times 2. But now notice that some of these numbers divide away. 2 divided by 2 is the number 1, and 2 divided by 2 is the number 1. And that's it. There's no more. There are no more factors that are the same on the top and on the bottom. Well, the numerator is 1 times 1 times 3, which is the number 3. The denominator is 1 times 1 times 2 times 2, which is 4. So this is the expression in lowest terms. Okay, so to reduce a fraction, we factor it out, we divide out what can be divided out, and whatever is left is our result in lowest terms. But a rational expression is just a fraction, which means that I'll be able to do the same thing that I see here. So, for example, here we're going to simplify the rational expression. We can also say we're going to write the expression in lowest terms. Those mean the same thing. Let's consider the following expression. X squared plus 3x divided by x to the power 3 plus 3x to the power 2 plus 4x plus 12. This is a rational expression. We're going to write it in lowest terms by following the same procedure that we always do for a fraction. We're going to factor, and anything that divides out will be divided out. All right, so let's factor this numerator. You'll notice that these have a common factor. They both have an x in common. Okay, so let's factor out that x. And when we factor out the x from each of these terms, we're left with an x and a 3. And notice that is the same. If you're ever in doubt whether or not you factored correctly, you can always multiply. X times x is x squared. X times 3 is 3x. Now our denominator is a little more complicated. You'll notice that there is no common factor among all the terms. These have x's, but that one doesn't. And these can be divided by 4, but not these. And these can be divided by 3, but not these. So there is no common factor for all terms. However, you'll notice that there are 4 terms here, which suggests that we might want to factor by grouping here. So let's go and do that off to the side. We're going to factor by grouping. We're going to take x to the third plus 3x squared plus 4x plus 12. And now we're going to take just the first 2 terms, factor out the common factor, which is x squared. That leaves us x plus 3 when we divide each of these by x squared. Looking at these 2 terms, they have a common factor of a positive 4. They can both be divided by 4. And when we do that, that's going to leave us an 1x, and 12 divided by 4 will give us a positive 3. And now looking at those 2 terms, this term in blue and this term in red, you realize you have a common factor between them. They both have an x plus 3 in common. So that's the common factor which we write in front. When I divide out by x plus 3, I'm left with x squared. And with this term, if I divide out by x plus 3, I'm left with a plus 4. So my denominator factors as x plus 3 times x squared plus 4. But notice now that my numerator and my denominator have a common factor. Just like over here, 2 divides 2 to give me 1. Here, x plus 3 divides x plus 3, which gives me the number 1. Okay. And let me go and cross that like that. So here the numerator is 1 times x, which is just x. My denominator is 1 times x squared plus 4, which is x squared plus 4. So these two expressions mean the same thing, but this one is in lowest terms, which incidentally, when we start looking at equations that involve rational expressions, whenever we start looking at things that use these within the problem, these two will mean essentially the same thing, but this one will be significantly easier to work with. Factor, divide out common factors, whatever's left multiplies back to give you your result. All right, so go ahead and give this a try. You're going to simplify the expression. Meaning you're going to write it in lowest terms. 6x minus 24 over x squared, make that cubed, x cubed minus 4x squared minus 5x plus 20. Go ahead and pause the video, give that a try, and once you've written it in lowest terms, go ahead and unpause and we'll go through it together. Alright, so let's take a look. We begin by factoring the numerator. Note that the numerator has a common factor. Both of these numbers can be divided by 6. Here we don't have a common x because this last term doesn't have a variable. But if we divide these two by 6, we're left with an x minus 4. Our denominator can be factored by grouping. That takes a bit of space. Let's go and do that off to the side. We take x to the third minus 4x squared minus 5x plus 20, and we group the first two terms. These have a common factor of x squared. If we divide each of these by x squared, we're left with an x minus a 4. Now if we look at the other two terms, notice they are both divisible by 5. Also note that the leading term is negative, so we will factor out that negative as well. So that's going to be a minus 5 as our common factor. And if we divide each of these by a negative 5, that leaves us just an x. And here a positive divided by a negative will be a negative. 20 divided by 5 is 4. So now looking at those two terms in blue and red, you notice they have a common x minus 4 in common. And when you divide by x minus 4, you're left with x squared. When you divide by x minus 4, you're left with minus 5. So here we're left with x minus 4 times x squared minus 5 in our denominator. And now notice that in the numerator and the denominator you have a common factor. These two divide out to give us the number 1. And so our numerator, 6 times 1, is 6. While our denominator, x squared minus 5 times 1, leaves us just x squared minus 5. And this is equivalent to this expression in lowest terms. Now, one thing to note here is I factored out a negative here. What if I hadn't factored out the negative? Well, then this would stay negative and this would stay positive. So here these would match, x minus 4 versus negative x plus 4. But by factoring out a negative, we changed the signs enough so that they did match. That can happen more generally for the entire expression. For example, let's say we're going to simplify something like this. We're going to take x minus 5 over 5 minus x. Now here, the numerator and the denominator don't really factor. They don't have any common factors. They don't fit the factor by grouping or the difference of squares or cubes or any of the other forms that we know. But here, they're not the same, so we can't divide them out. So it looks like there's nothing we can do. But here's where we realize that all the terms would be the same if only their sign changed. If this was a positive instead of a negative, and if this was a negative instead of a positive, that would perfectly match my numerator. What I can do is what I did up here. I can factor out a negative, which we mean a negative 1. If we factor out a negative 1, dividing this negative x by negative 1 leaves us a positive x. And dividing 5 by negative 1, a positive divided by a negative, will give us a negative 5. So by dividing out the negative 1, now this term in the numerator and the denominator divide out exactly. So here these divide out, leaving you 1 over 1. And so in the end, your result is, that's just the number 1 in the numerator. In the denominator, we have negative 1 times 1, which is negative 1. And then here these can be divided. A positive divided by a negative, that's a negative. 1 divided by 1 is still just 1. So those can be reduced that way. And that can be done in tandem with other factorizations. So for example, let's say we needed to reduce x minus 5 over 10 minus 2x. All right, we have a common factor in this denominator. So we could factor out, notice both these are even numbers, so they can factor out the number 2. And this would leave us 5, and this would leave us a minus x. Oh, but we notice that that's the opposite of what we wanted. We wanted all the terms to have opposite signs. Okay, so then instead of factoring out a positive 2, what we should do is, like we did up here, factor out a negative 2. So by factoring out a negative 2, what it looks like is that is now a negative 2 on the outside, and all of these have the opposite sign. If we factor out, if we take 10 divided by negative 2, that's a negative 5. And if we take negative 2x and divide it by negative 2, negative over negative is a positive x. And so now the numerator and the denominator have common factors. These divide out to give us 1 over 1. And so now our result is, that's the number 1 in the numerator. In the denominator, we have negative 2 times 1, which is negative 2. And there's our result, 1 over negative 2. So as an example here, go ahead and give this a try. Go ahead and reduce, simplify the expression. Two minus x squared over x to the third minus 4x squared minus 2x plus 8. Go ahead and pause the video, give that a try, factor and simplify, and once you're done, go ahead and unpause and we'll go through it together. All right, so let's give that a try. Here, let's go ahead and work on our denominator first. That's the bigger one. That has got 4 terms, so it looks like grouping is the correct thing to do here. If I take x to the third minus 4x squared minus 2x minus 8, grouping, that should be plus 8. Grouping the first 2 terms, I have a common factor of x squared. And if we divide each of these by x squared, we're left with x minus 4. Here, these two have a common factor of 2, but that leading term is negative, so we'll take out a negative 2. And that'll leave us with a 2 minus 4. Oh, with an x minus 4. And so now, this term and this term have x minus 4 as a common factor, which we can bring to the front as the common factor here. And when we divide each of these by x minus 4, we're left with an x squared and a minus 2. So our numerator has not been factored yet. Our denominator is x minus 4 times x squared minus 2. Notice that this x squared minus 2 looks almost exactly like this numerator, except the signs are wrong. Whenever you have something like that, where these are identical except for all the signs, and that's a positive versus a negative, and that's a negative 2 versus a positive, that's when you want to factor out a negative 1. So here, if I factor out the negative 1, that's going to give me Well, divide negative x squared by negative 1. That gives me a positive x squared. And divide 2 by negative 1. That gives me a negative 2. So now that those match, now that these can be divided out, we divide. That gives us 1 over 1. And so now our numerator, negative 1 times 1 is negative 1. Our denominator is x minus 4 times 1, which gives us x minus 4. And that's our result. So these two expressions mean the same thing, but this one is in lowest terms. If anybody has any questions, comments, or problems, please make a note of those and reach out. And I hope everyone has a nice day.